Artificial intelligence is a term which, for many people, I think, conjures up images of Hollywood movies, of killer robots, or perhaps even the more subtle but perhaps more sinister type of artificial intelligence we saw in HAL in the film 2001, in which it becomes increasingly paranoid and eventually kills some of its astronaut masters. That's the world of science fiction. But something very interesting has been happening over the last 5 years. And I think one of the evidence points for this is just some of the books which have appeared. These are all books which have been published in the last couple of years. And just look at some of the titles. Our Final Invention, Artificial Intelligence and the End of the Human Era. Superintelligence, Paths, Dangers and Strategies. The Artificial Intelligence Revolution. Will artificial intelligence save us or replace us? And even various luminaries have commented on this. Stephen Hawking has said, the development of full AI could spell the end of the human race. Elon Musk said, rampant AI is the biggest existential threat facing mankind. A somewhat pessimistic view of the subject, I would say. So this evening, what I want to do is to look at some of the reasons why we've seen this explosion of interest in artificial intelligence, to look at some of the science behind the technologies, and hopefully to paint a slightly more optimistic view of how AI might help humanity rather than destroy us. One of the things I want to do as well in this talk is to look a little bit at the history of AI, because the history is quite fascinating. And it goes back a long way, certainly at least as far as this person, Alan Turing. Now, I'm sure you've all heard of Alan Turing. He was a Cambridge mathematician, famous for many things, but amongst them, in the 1930s, he really laid the foundations for modern computer science. He, in a sense, conceptualized what today we call a digital computer, and he asked the following question: could such a machine emulate the capabilities of the human mind? Could a machine think? Well, he was largely left to theorize because he didn't have, in his day, the technology to take this forward. And really, the big development that has allowed us to think of artificial intelligence potentially as something of practical value is the development of the digital computer, the modern, in particular, the modern silicon computer. And this is a rather old silicon chip containing, well, a modern chip will contain billions of components. These chips are incredibly powerful. My laptop, for example, can probably do several billion operations a second. And here's an example of an operation. Take two 16-digit numbers, multiply them together, get the answer correct to 16 digits. So even this humble, rather ordinary laptop can probably do several billion, several thousand million of those per second. So what that machine is doing is it's slavishly following instructions. In this case, the instruction is to multiply two numbers together. But back in the 1950s, computer scientists working with machines far less powerful than this laptop wondered whether a set of instructions could be found to program a computer which would cause it to exhibit intelligence. So this is an example of such a program. This is from 1964. This is called ELIZA. It was developed at the AI laboratory at MIT. This particular script, this particular version, was a psychotherapist, and today we'd call this a chatbot. So you had a little conversation with the computer, and it would use various tricks. It would ask you for your name, and then it would call you by your name. And to many people, at least superficially, at least for a short period of time, it appeared that it was exhibiting something a bit like intelligence. Of course, if you interacted with it for more than a few minutes, you realized it was extremely dumb and was not in the slightest bit intelligent. But at least superficially, it seemed to mimic intelligence. And this field of artificial intelligence was tremendously popular back in the 1950s and the 1960s. And it was founded on the idea that computer scientists would be able to program computers to be intelligent. That is to say, to write a computer program or a set of instructions such that when the computer followed these instructions, perhaps blindingly fast, billions per second perhaps, it would exhibit intelligence. And there was a tremendous amount of hype, rather like there is today, a tremendous amount of excitement about artificial intelligence and its potential. However, that excitement didn't last forever. In fact, it didn't really last for very long. by the time we reached the 1970s, things began to change. And one landmark moment in the history of artificial intelligence was the publication of a report by Lighthill in 1973, in which he presented a very pessimistic prognosis for this field, which led to an almost complete cessation of funding, first in the UK and then elsewhere, and led to what some people have called the AI winter, where AI, artificial intelligence, became very unfashionable. Now, that report was a seminal report in the field, and shortly after its publication, the BBC televised a debate from this very lecture theatre from the Royal Institution, and I'm going to play a short extract from that debate. And this is hosted by Sir George Porter, who is the President of the Royal Society and also the Director of the Royal Institution.
Good evening and welcome to the Royal Institution. Tonight we're going to enter a world where some of the oldest visions that have stirred man's imagination blend into the latest achievements of his science. Tonight we're going to enter the world of robots. Robots like Shaky, developed by the Stanford Research Institute. Shaky is controlled by a large computer. He's directed through a radio antenna. Through a television camera, he gets visual feedback from his environment. The box appears on the monitor screen. The computer analyzes the traces which appear on the visual display until it can interpret them as an object it recognizes. Shaky gets tactile feedback through his feelers. He's able to move boxes with his push bar. He's programmed to solve certain problems that can be contrived in his environment, to choose, say, an alternative route to a certain point when his way has been blocked. Shaky is unquestionably an ingenious product of computer science and engineering. But is he anything more? Is he the forerunner of startling developments which will endow machines with artificial intelligence, enable them to compete with and even outstrip the human brain? One man who's pessimistic about the long-term prospects of artificial intelligence is our speaker tonight, Sir James Lighthill, one of Britain's most distinguished scientists. He's the Lucasian Professor of Applied Mathematics at Cambridge and has worked in many fields of applied mathematics. He's a former director of the Royal Aircraft Establishment at Farnborough. Last year, he compiled a report for the Science Research Council which condemned work on general-purpose robots. Not surprisingly, scientists who've been working on such robots have reacted strongly in defense of their field. Three of them are here tonight to challenge Sir James' findings. After they've had their say, the discussions will be open to bring in members of the audience here. With many mathematicians and engineers, computer scientists and psychologists among them, their contribution will be particularly welcome.
Particularly interesting to note how hairstyles have changed since 1973. So that was the beginning of the AI winter, and we had a period when it was positively unfashionable to work on AI or to say you were working on artificial intelligence. Nevertheless, of course, the field of computer science advanced with great rapidity, and there were many exciting developments. One that I'll draw attention to is in the field of computer programs that play chess. So in the heyday of old-fashioned artificial intelligence, chess was considered to be one of the pinnacles of human intellectual achievement. Surely, if a machine could play chess, everything else, like solving world poverty and global warming and whatever, would be sort of trivial by comparison. Well, it turned out that in 1997, a computer program, a chess machine called Deep Blue, built by IBM, beat the world chess champion Garry Kasparov. Now, what's interesting about this is the way in which it worked, because this machine was dedicated to playing chess. It did one thing and one thing only, which was to play chess, and it did it very well. And it did it by following a series of instructions, to analyze moves and responses to moves and to evaluate board positions. And it made use of the very high speed of digital computers. It would analyze literally millions of possible moves and counter moves in order to choose a good move for the machine. A more recent example, again from IBM, is the machine Watson, which defeated Ken and Brad, who were the two champions at this US television quiz show called Jeopardy. And so this challenge was conducted on live television. And again, very impressive. This is a sort of general knowledge question answering type of quiz. And Watson made use of information that it had pulled off the internet, including the whole of Wikipedia and much else besides. Again, tuned by a team of very smart people at IBM over a period of about 7 years in order to do this one very specific thing, which was to win at Jeopardy. And so we have, during this period, 2 examples, and there are other examples, of computers doing things which previously only humans could do, being able to do things better than humans, things which appear to be very intellectual in nature. But they're very specific. And of course, every time another task was completed by machine to a level greater than humans, people said, well, okay, that wasn't really intelligence after all. That's not really artificial intelligence. In fact, some cynics have actually said artificial intelligence is simply anything that computers can't yet do. So every time we solve another problem, we've not advanced artificial intelligence. And in some ways, that's fair, because one of the most extraordinary things about the human brain is not that we can do question answering or that we can play chess, but we can do all of these things, and we can learn to do new tasks. So there's something rather special that we haven't captured in the examples I've shown so far. But something very interesting began to happen about 5 years ago, and it concerns a field which has been around, as you'll see later, since, again, going back to the 1960s, the field of neural networks and the development of so-called deep learning. And a little bit later in this talk, I'm going to dive into some of the science behind neural networks and deep learning. But deep learning was developed by Geoffrey Hinton at the University of Toronto and other academics and colleagues around the world, and appeared to show great promise. And so an attempt was made to see whether this would scale to some sort of real-world problem. And back in 2012, Jeff and others from Toronto collaborated, in this case with Microsoft Research in Redmond, to apply deep learning to the problem of speech recognition. Now, speech recognition is a tough challenge. It had been around for many years. Performance of speech recognition systems, if you've tried one from 10 years ago, you'll know it's pretty bad. Could deep learning help with speech recognition? Now, at the time, there's a whole community of people working on speech recognition, people doing PhDs, going to conferences, publishing papers. But the performance, the error rate of speech recognition systems had been pretty much flat for an entire decade. Along came deep learning and immediately produced a 30% reduction in error rate. Now, that was dramatic if you think of all of the effort that had gone into this field over the previous 10 years. So this particular example, this is Rick Rashid, who is the founding vice president who set up Microsoft Research worldwide. He's seen here in Beijing. And he's illustrating the power of deep learning by giving a talk to a Chinese audience in Mandarin. Now, he doesn't speak any Mandarin. What's happening is that he's speaking in English, and that is being translated, or first of all, captured and transcribed into text by a deep neural network. That English text is being translated into Mandarin by another deep network. And then finally, a third deep neural network is taking that Mandarin and synthesizing speech, but using samples of Rick's own voice. So even though it's Mandarin, it still sounds a little bit like Rick. So that was a sort of seminal moment. These deep neural networks were not programmed to do this. They learned how to do this. They learned from data. So a very different approach to artificial intelligence. And this was a particularly moving occasion because there are about 5,000 Chinese students in the audience. Apparently some of the students were in tears at the thought that the language barriers might at last come crashing down. So that was interesting. But what's particularly interesting is that this one technique of deep neural network seems capable of solving many different tasks. So this was a British startup called DeepMind, and in 2014 they applied deep neural networks together with a technique called reinforcement learning to tackle some games, not chess this time, but some old Atari games, about 50 of them. And the neural network learns to play these different games by effectively a process of trial and error. So it makes random moves, it sees how its score is doing, it tries different things, and it gradually learns over a period of many, many games how to play the game successfully. In about half of the games, it achieves human-level performance. Now, what's interesting, it wasn't programmed to solve a specific game. The exact same architecture, the exact same software was able to learn to solve or play a whole variety of different games. So this seems much more like the capabilities of the brain, the ability to learn and the flexibility to learn new problems. DeepMind was acquired by Google, and in 2016, earlier this year, they used much the same technique, deep neural networks and reinforcement learning, to tackle a very much harder game, the game of Go. So this is a deceptively simple-looking game involving black and white stones on a simple grid of squares. But the combinations of moves is very much larger than in chess. So from a computational point of view, this is a very much harder problem than chess. And therefore, building a machine that achieved human-level performance had proven to be very much harder than with chess. And it was thought it would be at least another decade before that was achieved. So it's very surprising then when earlier this year, AlphaGo, as the program was known, beat one of the world's leading Go players, probably about a decade earlier than people had anticipated. So that's game playing, that's speech recognition, but much the same technique of deep learning can be applied to very different fields. Here's another historically very important example. This is called ImageNet. So this is a data set of the order of 1 million images, classified according to many different thousands of categories. And the goal is for a machine to take an image and to assign it to the correct category. So it needs to take the top left image as its input, and the output has to be the label judo, and not the label oceanfront, for example. Well, that's a tough problem, and people have been working on this for a number of years, and then they applied deep learning, and the immediate effect was to halve the error rate compared to any previous technique. So again, a very dramatic improvement in performance, and back in 2015, a deep neural network developed by Microsoft Research was applied to this data set and achieved the same error rate that a human makes. Now, I should say that one of the reasons the neural network is as good as a human is that it's better than humans at distinguishing 57 different varieties of mushroom, but it also makes some mistakes that we would think of as rather silly and perhaps no human would make. But nevertheless remarkable that this same architecture, this same concept can be applied to this very different domain and can achieve human-level performance. And so it's really that spectrum of different successes in many different domains that really has underpinned this explosion of excitement around artificial intelligence. So I thought I'd spend a little bit of time now looking at neural networks and deep learning and telling you a little bit about some of the science and some of the technology behind these successes. So neural networks, as the name suggests, are inspired, albeit loosely, by the human brain, and in particular by the neurons in the brain. So the interesting part of the brain are these electrically active cells called neurons. And here's a photomicrograph showing some of the neurons which have been stained, because they're very complex structures, lots of branches, and they make lots of connections with each other. And they send electrical signals to each other and thereby process information. Now, the human brain is often described as the most complex object in the known universe, and I just want to give you a little feeling for just how extraordinary the brain is. So this is a picture of South America, and outlined in red is the Amazon rainforest. And in spite of our best attempts to destroy it, it's nevertheless still absolutely enormous. You can see a picture of the UK for scale. I used to have a picture of Europe, but I've had to update it recently, unfortunately. Now, what's interesting is that the number of neurons in the brain is of the same order as the number of trees in the Amazon rainforest. But that's not really the interesting part. The really interesting part about the brain, not the neurons, but the connections between the neurons. These are called the synapses. And each neuron makes perhaps 10,000 connections with other neurons. And so the number of synapses in the brain, and the synapses are thought to be the seat of learning, and the number of synapses in the brain is of the same order as the number of leaves on the trees of the Amazon rainforest. So the brain is truly extraordinary. We certainly don't understand how the brain works, but our limited knowledge of how the brain works has been inspirational in developing a technology called neural networks. So here are two neurons. The neuron on the left, if it's stimulated in an appropriate way, can fire. It can send an electrical impulse down this cable, the axon. And that axon makes connections called synapses with other neurons and can stimulate those other neurons themselves to fire or can inhibit them from firing. And the strengths of those synapses can change as a result of the operation of the brain, as a result of processing information. So the brain has the capability to learn as a result of effectively the data that it sees, the inputs that it receives. And so going back as far as the 1940s, people began to build mathematical models of neurons and synapses and learning in the brain. And there are some very sophisticated models, but the ones that interest us are extremely simple ones. And we can describe them by this little picture. So the dots down the left-hand side represent inputs. If you like, you can think of those inputs from other neurons. And they're combined together to cause a neuron, here labeled Y, either to fire or not to fire. And the connections between them, labeled W, represent the strengths of those synapses. So this little model can be expressed mathematically, and this is the only equation in the entire talk, I promise you. But the equation captures this very nicely. It says that you take each of those inputs, xi, and you multiply by a weight, a strength, w, and that can be positive or negative, and you add them all up, you add up all those weighted strengths, and you pass them through this function sigma. And sigma just says that if the total combination of inputs is positive, the output is a 1, and if it's negative, the output is a 0. So you can imagine this little neuron being a little classifier. You can imagine those inputs being something that's extracted from an image, and perhaps the output says whether or not there's a face in the image. So our goal is to have this neuron output a 1 if there is a face, and output 0 if there isn't a face. And so we could imagine adjusting all those little weights, those parameters, those synapse strengths, if you like, using lots of examples of images of faces and images of not faces, until we have tuned those parameters in such a way the system has learned to solve that particular task. So that very simple mathematical model of a neuron is called a perceptron. And there was a lot of excitement and a lot of hype, again, around these very early neural networks back in the 1960s. And this is one of the pioneers of this field. This is Frank Rosenblatt, who in the late 1950s and early 1950s did a lot of work, both theoretical and experimental, on perceptrons. And what's interesting, of course, is he didn't have access to wonderful machines like this laptop. He couldn't just program these in software. So he had to build analog hardware instantiations of perceptrons. And here he is in front of some symbols at the back, the triangle, the circle, the square, shows a typical problem that the perceptron would be asked to solve. Could it distinguish between a circle and a triangle? Could it be trained to tell the difference between a circle and triangle? Now, the input to the perceptron was this box on the desk. This is an array of 20 by 20 cadmium sulfide photocells, photosensitive or light-sensitive resistors, which formed effectively a very primitive digital camera. These are like the pixels of a very slow, very low-resolution camera. And so here's a typical experimental setup. In this case, it's going to try to distinguish between some letters of the alphabet. This is, as I said, a very poor quality camera, so we need some very powerful lights shining at the object, and there's a lens that focuses the image onto those photocells. So the output of that camera then goes into this big rack of equipment, and what you see here are effectively the synapses of these neuron models. So in the rack here in this person's hand, each of those cylindrical objects is a combination of an electrical motor and a rotary resistor or potentiometer. So by a purely electrical process, the electric motor can change the resistance value. So the value of that resistance represents the strength of that synapse. And Rosenblatt invented something called the perceptron algorithm, which was a mathematical procedure by which those motors could adjust the strengths of the synapses in response to various inputs in order that the system could learn. So let's say we're distinguishing between triangles and squares. You present a triangle at input. If the output is a triangle, that's fine. But if the system makes a mistake and outputs a square, there's an algorithm for making little adjustments to all of those synapses to make the output closer to the desired value. Now you present another image. You present a square. If the output's a square, that's fine. If it isn't, you make some adjustments to the synapses. And so that perceptron learning algorithm allowed the system to learn by seeing lots of examples of each class, and it could gradually improve in performance and hopefully solve the problem. Now, there's a lot of excitement about these perceptrons because it turned out that they could actually learn to solve things like distinguishing shapes and letters of the alphabet and so on. And for the day, that was remarkable. But this wasn't just an empirical result. Rosenblatt also proved a theorem. She showed mathematically that if the perceptron was capable of solving a problem, that is to say, if there existed a setting of all of those resistors such that the system would solve the problem, then the perceptron was guaranteed to find that solution. So people got very excited about this. I'll just show you a little bit more of the structure of the perceptron. What you see, so on the right there are these racks of potentiometers. On the left, this jungle of wiring looks like it's just random. The reason it is just random. These are the inputs to those neurons. They're called features, and they're just little combinations of those pixels. We've got that 20 by 20 grid of photocells, the pixels, and each of the neurons would combine some inputs, so-called features, which were just little combinations, subsets of those pixels combined together in some fixed way. Chosen by the designer of the perceptron. And this particular, and there were lots of ways of choosing these, and lots of research was done. One way of choosing them was just to take random subsets of those pixels and combine them. And that's what this random-looking wiring is. And the reason this was interesting is that even though you'd randomize the inputs, the system could still learn to unscramble them and solve the problem. So that was sort of remarkable. And perhaps even more remarkable is you could take a pair of wire cutters, take a system which has learned, it's been trained to solve a problem, go in with a pair of wire cutters and cut 10% of the wires, and its performance would degrade a little bit, but it would continue to work. So a little bit like going down the pub, having a few too many beers, a few extra neurons die, the next day you can still function, maybe not quite as well as previously. We call that graceful degradation. It's a property which I'm pretty sure my laptop didn't have. I started cutting wires in my laptop. Very soon it would just stop working completely. So again, this is a little bit brain-like in some ways. So that generated a tremendous amount of excitement. And so let me just summarize what's going on here in a little picture. So on the left, the nodes or the units or the neurons, if you like, on the left-hand column, represent, in the case of the perceptron, those pixels, the original raw pixels, and the dots down the middle are what we call the features. So each of those dots would be some combination. It might be just the sum of a randomly chosen subset of those pixels. And that's represented by those green connections. So those green connections will correspond to that jungle of random-looking wiring. And that's fixed. So it'd be chosen by the designer at the outset, but then it's fixed. It doesn't change during learning. Then what we have is this red layer, and the red connections represent those resistors. These are adjustable parameters in this perceptron. And so the neurons or the nodes on the right-hand side, again, take combinations of some subsets of the features, but this time the strengths of the combinations are learned. Those are the adjustable parameters. So what you see is we have a layered structure. In fact, again, this is reminiscent of the brain. If you think of the visual processing in the brain, it goes through a series of layers of neurons. But the important thing is that only one of these layers is actually adaptive. Only one layer changes during learning. Now, perceptrons were interesting because they could learn to solve problems. That was tremendously exciting. But sometimes you would give it a very similar problem, which looked just as easy, and it would fail to learn. So what was going on? Sometimes they worked, sometimes they didn't. Well, these two computer scientists, Minsky and Papert, analyzed perceptrons mathematically, and they showed that there are some very severe limitations to the capabilities of perceptrons, that they are very limited in what they can do. And that limitation arises because there is only a single layer of adaptation. And they published this in this famous book called Perceptrons. And it's often said that the publication of this book led to a loss of interest in this alternative approach to artificial intelligence. So instead of programming the computer to be intelligent, here the system is learning to be intelligent. And this book, of course, is a piece of mathematics. People checked it, it was correct, so it was hard to refute. But the proof applied only to a single layer, to systems which have single layers of adaptive connections. At the end of the book, they conjectured that even if you had more than one layer, similar results would apply. They conjectured that these neural networks were never really going to be very useful. That part was a pure conjecture. So there we have the perceptron with a single layer of adaptation. The field of neural networks had been very exciting in the 1960s, and that had gone into abeyance, and people had lost interest as a result of the mathematical discussion of perceptrons and their limitations. Then something very interesting happened, which was the discovery of algorithms different from the perceptron learning algorithm, but algorithms which would allow networks having more than one layer of adaptation to be trained, techniques like so-called error backpropagation. And so people could now apply multi-layered systems to various problems and see if they worked. And they discovered that these systems were very much more powerful than the single-layer perceptrons. Now, for various technical reasons, it turns out that you can really only train a system with usually at most a couple of layers. But nevertheless, those systems were very powerful. They were capable of solving lots of problems that hitherto had been impossible, and led to the second wave of excitement around neural networks in the late 1980s and 1990s. Now, I began my career as a physicist. I did a PhD in quantum field theory, and then I went off and worked on the fusion program. So at this time, I was at Culham Laboratory in Oxfordshire as a theoretical plasma physicist working on nuclear fusion. And I read about the discovery of the backpropagation algorithm and these two-layer neural networks and their ability, their brain-like ability to learn to solve problems. And it reminded me of HAL, the computer, artificial intelligence. I thought this is tremendously exciting. My sense was that we were at the dawn of a new era. This was so exciting that I was actually going to change fields and change career. And I did that by taking neural networks and applying them to data that we were gathering from experiments. This is the inside of the JET tokamak, the world's largest tokamak. This is down in Oxfordshire. When this is operating, it would contain a hydrogen plasma at about 200 million degrees. And it's bristling, the outside of this is bristling with all kinds of diagnostics and lasers and magnetic measurements and so on. So for the day, we had a huge amount of data. We could analyze it in all sorts of interesting ways. And so I set about applying neural networks to analyzing this data. And I became so excited about this, I changed fields. I left physics and actually moved into the field of computer science. So those are the two-layer networks. They were very powerful, but they were a long way short of achieving human-level performance on some of the tasks of the kind that I've talked about. So these systems were deployed in practical applications. They were very useful, but I think it's fair to say they remained reasonably niche. What happened then is other techniques came along. There's a technique called support vector machines that was very popular, that achieved slightly better performance than these neural networks. And so for the second time, neural networks sort of went into decline. People lost interest a little bit, moved on to other techniques for so-called machine learning. And then about 5 years ago, there was something of a breakthrough. For a number of years, people like Hinton, who himself had been pivotal in the development of backpropagation and neural networks in the 1980s, two-layer neural networks, discovered how to train networks having more than two layers, in fact, having many layers. And so the term deep learning refers to systems which have many, many layers of processing. And this makes them extremely powerful, because if you think about a task such as taking an image and then describing what's going on in that image in English language, that's something which isn't going to be done in two simple steps. There'll be some very low-level processing, discovering edges in the image, discovering combinations of edges to make corners, discovering relationships between corners that make shapes, discovering how those shapes combine together to make objects, like faces, looking at shapes of faces, whether somebody's smiling or not, taking those and using those to generate words and combining those into sentences and eventually generating language that describes what's going on in that image. That's many, many, many layers of processing. And so we need to be able to train networks that are deep, that have many, many layers of processing. And so really this is the breakthrough that underpins the new excitement in the field of artificial intelligence. So here's an actual deep neural network. This is one that's used for image processing, for example, taking images and labeling them according to the objects that are present in the image. And these blocks represent groups of nodes or neurons. So in one of those blocks, there are many layers. Each layer is a whole grid of units, and the units make connections to patches or receptive fields in the previous block. So you can see the structure is pretty complex. But that whole system is adaptive, and that whole system is trained on large data sets. And so now we have neural networks containing thousands or even millions of adjustable parameters trained on millions or sometimes even billions of examples of data points. So that's a modern deep neural network. And I like this. This is a fairly geeky magazine called Wired. If you're in the IT business, you'll know Wired magazine. If you're not, you perhaps won't. But this was the front cover of Wired magazine from, I think, June of this year. It just says, the end of code. Soon we won't program computers, we'll train them. So behind all the, if you like, the hype, the excitement around artificial intelligence, there really is a very fundamental transformation happening in the field of computer science. And that's a transformation from programming a computer directly to solve a problem, that is to say a human or team of humans devising a set of instructions such that when the computer follows those instructions, it solves a particular task, and instead doing something very different. Writing a set of instructions or a computer program which allows the computer to learn and then training the computer to solve the task by using large amounts of data. So I view that as a very fundamental shift in the nature of computation. There's something else going on as well, and I illustrate it with this slide. I got asked some colleagues just to write the word uncertainty. What you see, of course, is the tremendous variability in human handwriting. And you can see from this example why it's so difficult to program a computer directly to do something like recognize human handwriting. There's tremendous variability. If you think of a little rule which describes the shape of a letter E, you'll very quickly find an exception to that rule. And so you can write another rule that captures the exceptions, but there'll be exceptions to the exceptions. And there's this combinatoric explosion of possibilities. And that's really what defeated old-fashioned AI back in the 1950s and 60s, plus, of course, the lack of fast computers. But there's something else going on as well. And in a sense, it's complementary to this idea of learning. So we're seeing a shift in computation, I think a revolution in computation, between software which is written by humans and software which is learned from data. So there's something else going on. Not only are we seeing a transformation in computation from software which is written by hand to software which is learned from data, but we're seeing a shift from software which is based on logic, that is, everything is 0 or 1, it's deterministic, to software which deals with uncertainty. It quantifies uncertainty. It deals with, if you like, shades of grey and ambiguity. So I'm going to show you a little demonstration, and this demonstration was actually designed really to illustrate this idea of uncertainty and to show you a modern view of machine learning. So I've shown you what I would think of as a traditional view of machine learning, adjusting these synapses, adjusting these parameters in a neural network to bring it closer and closer to the desired performance. But there's a very different view of machine learning, and it shows you the critical role played by uncertainty. So this is an example that would be very familiar to many of you. It's what we call a recommendation system. In this case, it's going to recommend films or movies to people. So this is a huge table, and each column of the table represents a different movie, and each row of the table is a different person. And our goal is to recommend movies to somebody which we think they might enjoy watching. Now, in a real system, we would certainly make use of features. So we'd make use of features of the film, for example, its length, its genre, is it a comedy or an action-adventure or whatever, who are the actors and so on. We'd also make features of the user, their age, their gender, their geographical location, other things we might know about them. And those are certainly very helpful in matching movies to people. But for the purpose of this demo, let's ignore those features. All we know are the ratings which people have given to movies. And so we know that a certain person has watched a particular movie and they like that movie. That's represented by the ticks in these boxes. So where a particular person has watched a particular movie and they've given it a positive rating. Of course, sometimes people watch a movie and they don't like it, and so they'll give it a negative rating. And so those are the crosses. Now, this is potentially a big table. We might have 10,000 movies and 10 million people. So this is an enormous table, and it's mostly empty because we don't have very many ratings. And our goal, effectively, is to fill in the blanks. So where a person has not yet watched a movie, we want to predict, will they like the movie or will they not? So I'm going to show you a demonstration of a system which solves exactly that task. It's based on machine learning. And this is a little demonstration system, although the actual technology behind this is used in real systems. And in this case, we've chosen a couple of hundred movies. And the system has already done a certain amount of learning based on the ratings of a few tens of thousands of people on these 200 movies. Now what it's going to do is make recommendations for me. So it's going to learn about my preferences. Now, I wasn't one of the people in the original data set, so it knows nothing about me at this point. So what I need to do is watch a movie and decide whether I like it or not. So let's say I've watched this movie, and let's suppose I do like it. Okay, so what it's doing now is it's reordering the other movies according to whether it thinks I'll like them or not. Now, the vertical position on the screen is irrelevant. They're just spread out vertically so you can see them. What matters is the horizontal position. So if a movie is close to the right-hand edge of the white region, if it's close to that green region, then the system is very confident that I will like the movie. And it measures that confidence using probability. So it assigns a high probability to my liking that movie. Conversely, if it positions the movie down the left-hand side of the white region towards that red edge, it's very confident that I won't like it. And if it's in the middle, it's sort of 50-50. It's really very unsure. And what you see is that most of the movies are clustered around the middle. There's a lot of white space down the right. There's a lot of white space down the left. And that's not surprising. The only thing it knows about me is that I like that one movie. That's all it knows about me. So it hasn't had much data from me to learn. And so it's really very unsure about most of this. So let's pick another example. Let's suppose I don't like this one. So now what we see is the movies are spreading out. Some of them are moving towards the right, where it's more confident that I will like them. Some are moving to the left, where it's more confident that I won't like them. And this, if you like, is the modern view of machine learning. It's the reduction in the uncertainty of the system as a result of seeing the data. And so I can carry on. I can pick another one. Let's say I like this one. Pick another one. I suppose I don't like that one. So now it's seen 4 examples. And now you see a very different picture. You see a lot of movies clustered down the right-hand side, very confident I should go and watch those. Ones down the left-hand side, pretty confident I won't like them. Most of the white space is now in the middle. There are a few that it's really quite unsure about. The Sound of Music, for some reason. I'm not... But nevertheless, you can see that it has learned from data through a reduction in uncertainty. So that I think of this as the modern view of machine learning. I'm going to use this demo to illustrate something else as well, which I think is really very powerful. I think it illustrates this very nicely, which is the concept of information. So there's a whole field called information theory. It was invented by Shannon back in the 1920s. And he provided a mathematical basis for the concept of information, and that really is foundational in modern computer science and information technology. And I can illustrate that by going to one of these movies down the right-hand side. So I pick one of these down the right-hand side. It's pretty confident that I won't like this movie. So let's suppose that I watch it, and it's pretty confident that I will like the movie. So let's suppose I watch it, and indeed I do like it. So watch what happens, watch carefully as I let go of the mouse button. Okay, I don't feel I'll pick another one. So it's confident that I'll like this. So let's say I do like it. Watch what happens. A tiny change. The reason is that there was very little surprise. There's very little surprise in that data. So there's very little information. But if I pick another one here that it's very confident I'll like, let's suppose that I don't like this movie. Again, watch what happens as I let go of the mouse button. Okay. So this time we see a dramatic change. In fact, it's now got rather confused again. A lot of things have gone back to the middle. So there was a high degree of surprise. I was really confident that I was going to like the movie, and I said I didn't. That was very surprising. In fact, Shannon defined information as the degree of surprise. Now, what's interesting is that this is, I think, a very nice illustration of the difference between data and information. Because in every case, the amount of data is the same. It's one bit or one binary digit. In order to say that I like a movie or I don't like a movie, I can assign it a 0 or a 1. So each of those, 7 ratings I provided so far is represented by one bit of data. The amount of data is the same. But the amount of information is very different. So if it's a movie on the right-hand side, that I like, the amount of information goes to 0 at the right-hand side. When it becomes certain that I like it, and I do like it, the amount of information goes to 0. And the amount of information goes logarithmically to infinity as we go across to the left-hand side. So it's a very nice illustration of the difference between data and information. Okay, and that's an example of what we call collaborative filtering, because people are collaborating together to help each other work out which movies they're going to like. So this quantification of uncertainty is based on a branch of mathematics that goes back certainly 350 years called probability theory. And the actual mathematical equations of probability are deceptively simple. It's a very beautiful and very elegant theory, and it's just a way of putting numbers behind uncertainty in a way that's very consistent. So probability is really the calculus of uncertainty. Now, there are really two kinds of probability. So if you were taught probability in school, you're probably taught probability as the limit of an infinite number of trials. So the probability that a coin will land heads, if it's a fair coin, is 0.5 or 50%. What that means in precise terms is if you flip the coin a number of times and you measure the fraction of times it lands heads, then if you take the limit, as you flip more and more times, as you flip an infinite number of times, that fraction, it will fluctuate around, but it will eventually converge to a value, and that value is the probability. We call that the frequentist notion of probability, because it's the frequency with which something occurs. There's another view of probability, which we call the Bayesian view, which in a sense is more general, because it encompasses the notion of frequency, but it applies also to things like one-off events, unrepeatable events. If we want to ask, what's the probability that the moon was once part of the Earth compared to being a separate body that was captured by the Earth's gravitational field? We can't sort of repeat the origin of the universe millions of times and see which fraction of the times, and so on. It doesn't make sense. It's a one-off event. But we're using probabilities to describe uncertainty. And it's interesting that we use the same terminology. And the reason we use the same terminology is that if you try to ascribe numbers to quantify uncertainty, those numbers obey some very simple equations, and those equations are exactly the same equations as obeyed by frequencies, things like coin flips. And so we use the same terminology. We call them probability. But this is a much more general definition. So I tried to illustrate it with this example. So here's a coin, but it's a bent coin. So when I flip the coin, it isn't going to land, it might land concave side up. Concave side up. More often than it lands concave side down, let's suppose. I don't know if that's right according to the physics, but let's suppose it is. So imagine that I flip this coin an infinite number of times. Look at the fraction of times it lands concave side up. That'll be 60% or 0.6. That's the probability of landing concave side up. So that's a frequentist probability. But let's suppose that one side of the coin is heads and the other is tails. But imagine that you don't know which side is heads. You don't know whether the concave side is heads or the convex side is heads. But let's suppose I ask you to take a bet. I'm going to bet £5 according to whether it's heads or tails. Which way should you bet? Well, from your point of view, it's symmetrical. You don't know which side is heads or tails. So even though you know it's going to land concave side up more often than concave side down, because you don't know which is heads and which is tails, it's symmetrical. And so if you're acting rationally, you will bet according to a probability of 0.5. It doesn't mean that you believe that in the limit of an infinite number of trials, it will land heads 50% of the time. You believe that it will either land heads 60% of the time, or it will land heads 40% of the time, but you don't know which. So in a sense, the frequency with which it lands concave side up in that case is a bit like a frequentist probability, but this uncertainty over which side is heads or tails, it's a one-off event. One side is heads or the other is heads. It's not a repeatable event. It's a one-off thing. You just don't know which it is. That's like this quantification of uncertainty, this Bayesian view of probability. Now, at this point, you might be thinking, well, I'm making a lot of fuss here because we've had just a tiny change. Instead of having zeros and ones, we've now got numbers between 0 and 1. It seems like a very small change. I'll just give you one little illustration of the fact that probabilities can behave in very peculiar ways. So this is not a trivial change at all. This is really quite, I think, quite significant. So here's a little example. Here's a bus. And let's suppose that the bus is longer than the car. And there's a bicycle. And suppose the car is longer than the bicycle, then if the bus is longer than the car and the car is longer than the bicycle, then I think you'll all agree that the bus must be longer than the bicycle. Does anybody not agree with that? Good. Mathematicians call that property transitivity. So these, if you like, deterministic numbers, these certain numbers, these lengths of objects, behave in this transitive way. But if we now go to uncertain quantities, we discover that they can be non-transitive. And this is extremely peculiar. And it's not just a theoretical thing. These are non-transitive dice. They're very easy to construct. They're just regular dice. The only unusual thing about them is the choice of numbers on the faces. So these are unbiased dice. They can land on each of the 6 sides with equal probability. But the choice of numbers is a bit unusual. A particular number only appears on one of the dice, and so you can never have a draw. So if you roll one die against another, one of them will always come up with a higher number. We'll call that the winner. And what you discover is that if you, let's say, roll the red die against the yellow die, then 2/3 of the time, the number on the yellow die will be bigger than the number on the red die. So the yellow die actually just has 3s, so it always comes up with a 3. The red die has a couple of 6s and 4 2s. So 2/3 of the time it rolls a 2, and 1/3 of the time it rolls a 6. So 2/3 of the time, yellow beats red. Okay, that's fine. 2/3 of the time, likewise, purple will beat yellow. 2/3 of the time, green will beat purple. We'll come up with a higher number. And now here's the amazing thing. 2/3 of the time, red will beat green. So you can equip yourself with a set of non-transitive dice. I sell these at very reasonable rates, by the way. And you can have a very profitable evening down the pub with your friend because you show them these dice and you say, you examine them to your heart's content. Now you pick whichever you like, and I'll pick one, and of course you pick the next one in the sequence. You say, let's do the best of 11 or best of 15 throws. Bet £5. After a reasonably large number of throws, it's very, very likely that you'll win the bet. So they get a bit cross, and they want the die that you've just used, and so of course you pick a different one, and so on, and you'll always win. So this is just one of many, many examples of the fact that probabilities behave in very unusual and very peculiar ways. So we've seen the idea that artificial intelligence is being revolutionized by learning from data, and that learning from data happens through the quantification of uncertainty. So learning from data is one of the key ideas. So these algorithms, things like deep neural networks, are one of the foundations of this revolution. Another of the foundations, obviously, is the data. The explosion that we're seeing in data is one of the things that's enabling this revolution. The amount of data in the world is doubling on a very short timescale, probably less than a year. And so we're seeing a tremendous growth in the amount of data that can be used to fuel machine learning. There's a third ingredient as well, and that's computation. So these techniques are very hungry for computer power. So today we use neural networks with millions of adjustable parameters trained on millions or billions of data points using extremely powerful computers. And these computers live increasingly in what are called data centers. So here's a picture of a data center. This particular one is a Microsoft data center somewhere in North America. And what you see are these low buildings with no windows, and inside are racks and racks and racks full of computers and storage and networking. So these are really the world's most powerful computers these days. Now, these data centers are the foundation of what we call cloud computing, the idea that computing is now increasingly centralized in these data centers and accessed anytime, any place from any device. And there's a tremendous growth in cloud computing, and many companies, including in particular Microsoft, are expanding these data centers. And this data center, if you look closely at the top of the picture, you'll see some bulldozers and some construction work going on because this data center is being expanded. But if we fly around 180 degrees and look from the other end, you'll get some idea of the scale of expansion. So this particular data center is obviously increasing in size by an enormous factor. And so all around the world, new data centers are being constructed all the time. We're seeing this tremendous growth in the capacity of these data centers. Now, the last few weeks have been very interesting. There have been some very interesting announcements in the last few weeks. And in particular, the announcement by Microsoft of the world's first exascale supercomputer. And it's based on a technology called FPGA, or Field Programmable Gate Array. So the way to understand what this is think of it as a hardware chip, but where the architecture of the hardware can be changed using software. So it's a very flexible kind of chip. The chip itself is not as powerful, as fast, as a fixed architecture chip, like a central processing unit in this laptop, but it's very flexible, and so we can change the architecture and run and try out lots of different kinds of algorithms and neural networks and so on. And so in these data centers, as well as the regular computation, we've been deploying these field programmable gate arrays on a very large scale, to the point where a couple of weeks ago we announced the world's first exascale AI supercomputer. So an exascale means it can do an exa operation per second. That's 1 billion giga operations per second, or 1 million operations per second. I'm sure this won't end up being the fastest computer. There's more to come. So this is just an extraordinary growth in processing power, coupled with data, coupled with these new algorithms, is driving all of the excitement around machine learning and artificial intelligence. What's this being used for? Well, many different things. One example, of course, is personal assistants. Many organizations are working on, large companies are working on developing personal digital assistants. This is Microsoft, this one called Cortana. And these technologies are at a very early stage of development, but I'm very confident that over the next decade we'll see the capabilities of these types of assistant advance very, very rapidly. And there are many other applications of machine learning. And the technology continues to advance at a tremendous pace. So again, just in the last week or so, an announcement, in this case again by Microsoft, of the achievement of human parity in speech recognition. So this is an automatic speech recognition system which achieves the same error rate at the word level as a human transcriber. When humans transcribe speech, they make a few errors, so do the machines. The error rate is now the same. What else are we using this for? Are we building killer robots that are going to wipe us all out? Well, there are actually many more useful things we can do with this. And I'll just briefly tell you about a research project that we're looking at in Cambridge, at Microsoft Research in Cambridge, called Project Inner Eye. And this is using these machine learning and artificial intelligence techniques to look at the treatment of cancer. So what we see on the left is a cross-section of an MRI scan of a brain tumor, a very nasty brain tumor, and the radiologist is using a mouse and looking at this image and segmenting the tumor. That is, defining the boundary of the tumor by hand in order that this can be used for radiation therapy planning, firing in X-rays and radiation to try to kill the tumor and do the minimum damage to the surrounding tissue. So that's being done by hand and is a very time-consuming process. But we can use these machine learning techniques to speed this up and also to improve the accuracy and reproducibility of this. So a little bit of human intervention now to provide some initial segmentation. And after about 10 seconds or so, the segmentation is complete and it's more accurate and more reliable than the human segmentation. And this is a nice example of artificial intelligence being used in partnership with humans. So it's the case today, despite all the advances I've talked about, it's the case today, and I think it'll be the case for quite some time to come, that the capabilities of machines are different from and complementary to the capabilities of humans. So here the radiologist, with their experience of looking at these images, many different images from many different patients over many years, has built up a good qualitative understanding of the tumor, the nature of the tumor, how it should be treated. What the computer is good at is this three-dimensional segmentation, defining accurately and reproducibly which of those three-dimensional pixels, those voxels, is tumor and which is normal tissue. I started my talk with a rather gloomy outlook of killer robots. I think that belongs firmly in the world of Hollywood. But nevertheless, this is a very powerful technology. It's a very general-purpose technology. And as it's deployed, and I'm sure it will be deployed in many ways which are of enormous benefit to society, helping us as a species tackle some of the tremendous problems that we face in the 21st century, well, we must, of course, expect a few bumps on the road. And to help us think about issues around privacy, around security, around the implications of this transformation to the world of solutions which are learned from data. Again, we just announced in the last week or two the formation of the Partnership on AI, where some of the leading organizations working on artificial intelligence at large scale have come together to work together to see how artificial intelligence can best be used for the benefit of society. And finally, if you're worried about killer robots, I think we'll always remain in control. Thank you very much.